Hi Rockridge, this is Mrs. Berger, and today, day 6 of Unit 7, we'll be discussing geometric sequences in series. Last class, we talked about arithmetic sequences in series, which were those series that, to get from one number to the next, we had a common difference, even though sometimes it was adding the same thing every single time. We always called it the common difference between those next numbers. Today we're going to have a common ratio, something that we're multiplying by every single time, so common ratio. So we are going to have our formula sheet available to us for this. This time we're looking at the right side of the formula sheet because we're talking about geometric sequences in series, so we'll not really be talking about the arithmetic side of the page today. And again, we do have our definitions available to us on this formula sheet, so if we ever forget what these things mean, we can always take a look at those definitions on top. So let's get right into it. Let's look at some examples. So again, a geometric sequence is one whose consecutive terms have a common ratio. So what number is being multiplied every time? So if we had the sequence 1, 5, 25, 125, 625, obviously the common ratio that we're multiplying by every time is positive 5. So if we take a look at these, I'm already telling you that they are geometric. If you take a look at these, to get from one term to the next for this question A, we are multiplying by the same number, and that number that we're multiplying by is 3. It's helpful to see that when we have these little formulas, whatever number is being brought to the power of n, or the number of terms that we're on, that's always going to be our common ratio. Letter B is a little bit trickier to get from negative 3 to 1, and then from 1 to negative 1/3, and then from negative 1/3 to 1/9. First, we hopefully are noticing a pattern between the negatives to positives. And the only way you can switch between negatives and positives is if that thing that you're multiplying by every time is negative. So we know that much. And hopefully you'll see not only from the pattern that you're seeing on the left, but also this right here, that common ratio of 1/3 is what's common to everybody. You're multiplying by negative 1/3 each time. So instead of thinking about this as dividing by 3 or dividing by negative 3, you should think of this as a common ratio of negative 1/3, the thing that you're multiplying by every time. So let's get into using our formulas. If we are told find the 20th term of the geometric sequence, given that the first term is 4 and the common ratio is 2, remember that the notation for this is I'm trying to find the 20th term. A sub n is a sub 20. And if you look above at our formula, we need the first term, we need the common ratio, and we need to know which term we're talking about. So the first term we were given is 4, and then we multiply that by the common ratio, which we were told is 2, and we raise that 2 to the 20 minus 1 power. Now, one of the biggest things that people mess up on this is they try to multiply 4 times 2 and make it 8 and then bring that to the 19th power. That is not what we're asking you to do here. We're asking you to bring 2 to the 19th power first. Remember PEMDAS, remember order of operations. 2, your exponent must be addressed first. 2 to the 19th power times 4 is how you'll get your final answer, and hopefully, since you've had time to calculate this, you should get 2,097,152. One thing you'll notice about geometric sequences in series is they grow much faster than when you just add the same thing every time, and that should make some sense to us since we understand what multiplying means versus adding and subtracting. Find the 11th term of the geometric sequence, whose first 3 terms are 5, 15, and 45. So this time we were given the first term once again. So remember the first term, a sub 1, is 5. A sub 2 is 15. A sub 3 is 45. So I just wrote that out just so we can visualize what we're looking at here. So 5, and then 15, and then 45. Now we were told the first term, so we needed that for our formula. But we also need one other thing for our formula, and that's the common ratio. They didn't give that to us like they did in the first question, but we can figure it out. What are we multiplying by every single time to get to between the terms? Hopefully you're screaming at the video, it's 3. Yes, of course it's 3. We were asked to find the 11th term, so we'll use our formula now. Our first term was given to us as 5. We just figured out our common ratio is 3. We need to bring that 3 to the n minus 1 power, or the 11 minus 1 power. So you're going to bring 3 to the 10th power first, and then multiply by the 5. Hopefully at that point you should say the 11th term of this is 295,245. Okay? So that's just implementing our formulas, understanding what we're looking at, and understanding how to pull out R and the other terms like that. So sometimes you'll be asked not to come up with the term itself, but to write a rule, right? Write a generic rule that anybody coming along can figure out whatever term they're looking for, given some information. So if we're told one of the terms of the geometric sequence is a sub 3 and that value is 5, I immediately, whenever I am told something like that, I immediately try to get myself sort of in the map on this. I say, alright, I know the third term is 5. And I know my formula always needs the first term. So I'm going to have to figure out what that is, but let's see what other information they gave us. The common ratio is 2, so R equals 2. So that's going to be helpful in counting backwards to the first term. And of course they asked us to write a rule for the nth term. So they want us to write a generic rule for this geometric sequence, and we know those come from knowing the first term, the common ratio, and n minus 1. So we need two things, because n is going to be left open for the person to come along and use it. So we're going to leave that n minus 1 alone, because we're going to leave that for the person to enter when they figure out what term they want. But we need to input a sub 1 and r. Now obviously they gave us r, but we need that first term to finish this off. Well, if the common ratio is 2, and somebody multiplied something by 2 to get to 5, we can count back to this term that came right before 5 by dividing by 2. If we need to go backwards in a geometric series, we would divide by 2. So that would be 5 halves. Let's double check going forward again. If I multiply 5 halves by the common ratio of 2, will I get 5? Yes, I will. So I've done that count backwards correctly. Now let's count one more back. What did I have to multiply by 2 to get 5 halves? Well, I can also figure that out by dividing by 2. So if I divide 5 halves by 2, that would give me 5 fourths. Remember, 5 halves divided by 2 is the same thing as 5 halves times 1 over 2. So that's why I got 5 fourths. So my first term, and again, let's double check this, right? If I multiply 5 fourths by 2 over 1, will I get 5 halves as my second term? Yes, I will. So I've counted backwards properly, and now I have all the information I need to make my formula, or my rule. So for this particular case we're talking about, we have a term number 1 of 5 fourths, we have a common ratio of 2, and the user will put whatever number they need in to figure out what term they want for n. So that's our rule with that information. So let's see, if you would like to pause the video and try this on your own, please do so, but I'll go ahead and walk you through now. So write a rule for the nth term of this sequence. They didn't give us much more than these numbers, but we need to back into some information. Now clearly this is a sub 1, so they gave us a sub 1 without actually naming it. That's the first term. Now what is everything being multiplied by to get to each of these? You may have to think about this for a minute. Pause the video and think, what do I have to multiply by every time? What do I have for an r value? It may take you quite a while. I'm going to go ahead and give it to you now, but if you want to keep thinking, please pause it and keep thinking. But you will have come up with 3 halves. And it's not negative 3 halves because we are staying negative the whole life of this. We're not switching back and forth. So it's going to be a positive number that we're multiplying by every time. And it looks like we're dividing by 2 and multiplying by 3 each time. That's probably a little bit trickier than what you'll probably see on a quiz or a test, but be prepared to have that level of thinking. So now that I have r and a sub 1, I'm ready to write my generic rule. A sub n equals that first term, negative 8, times my r value, 3 halves, raised to the n minus 1. And that's all we can do. The n is ready for the user to put whatever value they want. If they want the 11th term, they'll enter 11 for n. If they want the 200th term, they'll put 200 in for n. But that's the rule that they'll have to follow. Alright, recursive sequence. So recursive sequence is definitely something that you could be quizzed or tested on. And it's something that we use that is not arithmetic, nor is it geometric. So the way you can identify these is you're looking from term to term to term, and you're not seeing the same number being added or subtracted every time. You're not seeing the same number being multiplied every time. It's something else going on. What's going on with a recursive sequence is if the next term depends on the value of the previous term, that's called recursive. So if you're looking at term number n, and you had to look back at the one that came right before, term n minus 1, that means you're looking at a recursive sequence. So if you need to, pause the video and take a look at this first one and see if you can see the pattern that's coming out here. How do I get from 5 to 4 to 9 to 13 to 22? And the clue I have is the previous term has something to do with how you come up with the next one. Pause the video if you need to. If you're coming back, or if you aren't patient enough to pause the video and think about it, hopefully you saw that to get from 5 to 4 to 9, you had to add 5 and 4 to get 9. And to get from 4 to 9 to 13, you had to add 4 plus 9 to get to 13. And so on and so forth. 9 plus 13 gets you the 22, and 13 plus 22 will get you your next term. So your next term is going to be 35. And now to notice, I'm not able to find the next term until I figure out that 35, right? So the next term is 35. Then I would add 22 plus 35 to get 57. Then I would add 35 plus 57 to get 92. So the hardest part of that one is finding the pattern, and then it's just a matter of figuring out how many more terms they want us to list. Sometimes instead of giving us a list of numbers, they tell us sort of the formula to follow, and so that's what the next one looks like. They're telling us the 0th term, and that is a thing. You can have a 0th term. The 0th term is 1, and the formula to find any term that you're looking for is a sub n equals a sub n minus 1 plus 4. I think the trickiest part of this is the notation. People have a hard time understanding what that means. This means previous term. So if you're trying to figure out the nth term, this is saying look at the one that came just before and add 4 to it. Okay? So let me show you what this looks like. If the 0th term is 1, which is what was given, to find term number 1 equals the term 1 minus 1, which is 0, so the 0th term, which we know is 1, plus 4. So the first term, or a sub 1, is 5. To find the second term, again, look at my formula. It says that in order to find a term, if I'm trying to find a sub 2, I need to look at a sub 2 minus 1, which is a sub 1, which is 1. So the first term, a sub 1, I just calculated to be 5. 5 plus 4 is 9. So the second, or a sub 2, must be 9. If you don't need to write this work off to the right, if you kind of see what's going on here, you can look at the term that just came right before. So if I need to know the third term, I look back at the second term and add 4 to it. If I need to find the fourth term, I need to go back and look at the third term and add 4 to it. If I need to find the fifth term, I need to look back at the fourth term and add 4 to it. That's what this formula is saying. This formula is saying, look back at the term that came right before the one you're working on and add 4 to it. So hopefully you realize that if you want the sixth term, go look at what the fifth term was and add 4 to it. That's what that formula says. And that is called a recursive sequence. It's not geometric or arithmetic, it's recursive. Alright, similar to what we had for arithmetic, we not only want to know which term, the number of terms that are in there, but we also want to add the terms together and find the sum of the series. We have formulas for that as well. You can flip back to that table of formulas. Those will be available to you. Anytime you want to find the sum of the geometric series, you can certainly look at the formula and say, alright, I know that this number right here that's being brought to the power of the term is going to be my r. So r, because it's being brought to the power of the input term, that's got to be my r. That's how you identify r. Now, without the formula, let's not do this with the formula. Let's understand, without the formula, we need to input, so to find the sum of this, we need to input a first value of 1. So 2 times 5 raised to the 1 power. That's the first term. Then we need the next term, which is calculated by raising 5 to the second power and multiplying by 2. Then we need the third term. Remember, this is my first input, this is my last input. So my third term is 2 times 5 to the third power. Then I need my fourth term. Remember, I have to go to the sixth term because that's what this formula says. It says go from 1 to 6. So then I need 2 times 5 to the fourth power. Then I need 2 times 5 to the fifth power. And finally, I need 2 times 5 to the sixth power. So I find out what each of those terms is, and I add them together on my calculator. If you need to pause the video and do that, please go forward and do that. And when you finish adding those all together, so calculating, make sure you raise that 5 to the power before you multiply by the 2. Remember to follow your order of operations. You will come to 39,060. That's the sum of that series. With the formula, the way you use the formula that you see on your front page, first of all, you know you have 6 terms. You have term 1, 2, 3, 4, 5, and 6. So you have 6 terms. So the sum of this 6-term series is found by taking the first term. The first term is here. The first term is 2 times 5 raised to the 1 power. So the first term is 10. And you multiply that by 1 minus the ratio. We said the ratio is 5 to the 6th power, because that's what's brought to the n power, divided by 1 minus r. So that's the formula. That's implementing the formula based on the information we were given in the summation symbol. If we do this by hand, we've got 10 times negative 15,624 on the top and negative 4 on the bottom. And then a final calculation will get us to 39,060. So thankfully, doing it by hand as well as doing it on the multiplying it out gets us where we need to be. Also recall that we can get our calculators to help us with this. So we can go to the math menu, we can go to the summation, and we can fill in, and it doesn't matter what letter you put in there. I don't bother trying to find the I button. I know the X button. I know where it is very well. So when X comes from 1 to 6, and the formula is 2 times 5 to the X, that's my input, right? The summation will come out to be 39,060, and it'll confirm our work. So if you have a geometric series or an arithmetic series, as long as you input it into the calculator, you'll be able to get your answer, or at least confirm the one that you worked on. Alright, find the sum of the first 10 terms of this geometric series. They tell us a few numbers in it, but they don't tell us some pertinent information. We're going to have to work out some pertinent information. So first of all, the first term that's necessary in our formula, right? A sub 1 is necessary. We also need to know what r is. So what are we multiplying by every time to get from term to term to term? Hopefully you see that r is 5. To find the sum of the 10 numbers, the first 10 numbers, we take the first number, which is 1, and multiply it by 1 minus r, which we calculated to be 5, raised to the 10 power, because we're looking for the 10th term, the sum of the first 10 terms, over 1 minus 5. That's how you would implement that formula. Make sure you've got your formula sheet next to you, or you're flipping back and forth to that front of the page to see which formula I'm working on. I am looking currently at the summation formula that's right here for geometric. Okay, so that's the one I'm using as I'm filling it in. Now we've just got some calculator work for us, right? So we need to work out that this ends up being 2,441,406. That is the sum of the first 10 terms in that series. So you can certainly see that geometric series grow very, very quickly. 2,441,406. let's take a look at part C. Again, you are welcome to put this one into your calculator. If you want to, if you forget where this button is or something goes horribly wrong with your calculator in the middle of the quiz or test, you can certainly work out what the different components of the formula are. So if I need to know what the first term of this is, I put my first input in. So to find the first term, I put my first input. My first input this time is a 0. So I calculate, alright, first term of this is 10 times negative 1/2 to the 0 power. Anything to the 0 power is 1. So this must be 10. My first term in this series is 10. That's important for the formula. I also notice that the thing being brought to the power each time is negative 1/2, and so that's how I can identify r equals negative 1/2. That's always where we look for the common ratio. Now let's be careful how many terms there are in this one. If I input 0, a sub 0, that's the first term, so that's 1. A sub 1 is the second term, a sub 2 is the third term, and so on and so forth. So if my final input is 7, because I have to go up to 7, count how many terms I'll have. 1, 2, 3, 4, 5, 6, 7, 8. There are actually 8 terms total because I started at 0 instead of starting at 1. So if I'm trying to find the sum of the first 8 terms, my first term is 10. I have a little bit of a mess here, right? I've got 1 minus negative 1/2 raised to the 8th power. This is from my formula sheet. Over 1 minus 1/2. It's a bit of a messy piece of work here. So 425 over 64 is what I was able to simplify that down to. If you want to put the decimal version of that, that's fine. And of course, we can always do our calculator. You can ask our calculator, hey, if I do math summation, and I go from an x value of 0 up to an x value of 7, and I've got 10 times 1/2, oh, that was negative 7, sorry, negative 1/2, and that is raised to the x power, right? I probably did something wrong. Let's see. We have a syntax error. Sorry about that. I had a syntax error. I was putting my power in the wrong place. So if I input my summation as was originally given to me, 10 times negative 1/2 raised to the x power from 0 to 7, I get 6.64 spit out, which matches what we had from our manual formula of 425 divided by 64. So if you carefully input this and keep the syntax correct, you can certainly make it through here with your calculator. Since we're in our calculator already, for question D, we have a summation, so let's see if we can do that one here as well, and then we can try the formula as a backup. So if I go Math menu, Summation, and in question D, I'm going from 0, oops, sorry, I'm going x from 0 up to 12. And the formula that's in there is 0.01 times 3 to the x power. My calculator is saying it comes to 7,971.61. Similarly, if I do this by hand with the formula, I need to be able to identify that the item being brought to the power is r, and the first term needs to be calculated. So my first term happens when my first input is put in. So 0.01 times 3 to the first input. My first input is 0. So that means 3 to the 0, which is 1. So the first term is just 0.01. Therefore, if I wanted to use my summation formula, I'm going from term 0, an input 0 to an input 12. So I'll have a total of 13 terms that I need to add all together. The formula says first write your first term, so that's 0.01, which I just calculated, times 1 minus your common ratio, that was 3, raised to the 13th power, over 1 minus 3. Make sure you carefully enter this into your calculator, or do each step at a time, and you'll come to the same exact number that our calculator did with the summation notation, 7,971.61. Now, we're going to talk about infinite geometric series. Let me pop back to our formula sheet to explain the difference. We just used the S sub n formula because there was always a finite number of terms that we needed to add together for these geometric series. We can also calculate an infinite series, believe it or not, an infinite series, a series that goes on forever. To identify that, or to talk about that, we need to look at what it actually means. An infinite geometric series, one that goes on and on and on and on and on. There's a little rule that we need to remember. If the absolute value of r is greater than or equal to 1, then we can't do that. That infinite series has no sum. So we actually don't have to do any work. We would just declare, nope, no sum. We don't have to do any manual work. But if the absolute value of the common ratio is less than 1, then we can calculate it, and we'll use the formula for the sum of the infinite series. So this little check, and it'll be printed on your formula sheet for you. See what it says here? Only use me if the common ratio, if you take the absolute value of the common ratio, if that number is less than 1. Basically, if it's a fraction or a decimal. If your r is a fraction or a decimal, you can go ahead and use the infinite geometric series. If it's not a fraction or a decimal, if it's 1 or more, if it's 1 or 2 or 3 or 3.5, then you don't have a sum for that infinite geometric series, and you would just write no sum. So let's take a look at this. Question A. Let's first determine what r is, because without knowing what r is, we can't really determine if we need to use the formula or not. To get from term to term to term in letter A, it appears to be multiply by 2 every time, right? Multiply by positive 2 every time. Now, for this r, the absolute value of 2, of course, is 2, which is definitely greater than 1. So that means there is no sum for this infinite geometric series. For letter B, the thing we're multiplying by every time, hopefully you can see that we are multiplying by 1/2 every time. And the absolute value of 1/2 is, of course, just 1/2. And that is definitely less than 1. So we do have a sum for that infinite series. And the calculation for that, we use our formula that we had printed on the front. Calculation for that is 1 divided by 1 minus 1/2, right? That formula says take the first term and divide it by 1 minus your common ratio. The first term was 1, and then r was 1/2. So when you do that, that's 1 divided by 1/2, or 1 times 2 over 1, which is 2. The sum of that series is 2. Now, a word of caution. I know you're very excited about using your calculator for these. Please don't ever, 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 ever try to do an infinite sum on the calculator, okay? It will churn and churn and churn and basically steal all of your quiz or test time from you, and it will never get to where you need it to be. The calculator does not work very well with infinity. You don't try to fake infinity. Don't try to put, a really, really gigantic number in there to try to sum your infinite series. Just do this formula. It's a fairly simple formula. Go ahead and do your formula by hand. The hardest part is making sure that you actually do need to do the formula, right? So determine that r, figure out if the series has no sum, or if it does, and then go ahead and implement your infinite series formula. Now, a quick note, the sum of this series, if you add 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, notice that your sum actually gets closer and closer and closer to 2, which we said was the answer to this. It's actually never going to quite reach 2, right? If you added 1 plus 1/2, that's 1 1/2, plus 1/4, that's 1 3/4. plus an eighth, you'll see that you're adding a little tiny little chunk every little time, and it'll eventually get very, very, very close to 2, but it's actually never going to reach 2. But we still say the sum is 2 because it's close enough. Okay, so if some of you are bothered by the fact that, wait a second, if I just keep adding a smaller and smaller fraction, I mean, yeah, I'm going to get close to 2, but I'm never going to reach it. That is true. But we're going to say, for purposes of our problems, we're going to say it is eventually going to get pretty much to 2 if we go on, if there is such a thing as going on forever to infinity. Okay? So let's do a couple more examples and then we'll wrap up for today. Now, like I said, do not enter this into the calculator. Do not enter infinite series. Don't try to fake infinity with a huge number. It's not going to work. It's just going to break your calculator. Not break it, but make it churn forever. So let's look at this. The thing being brought to the power is 0.6. So the thing being brought to the power is 0.6. So 0.6 must be the r. We do need to sort of take a look at what the first term is. So the first term is when we put the first input in. So if we put the first input in, that's 4 times 0.6 to the 1 minus 1. 1 minus 1 is 0. 0.6 to the 0 power is 1. So 1 times 4 is 4. So the first term in this is 4. And really that's all we needed to get through this summation, right? The sum of an infinite series. Now, the r being 0.6, that's nice because that's less than 1. It's a decimal or a fraction. So I'm good to go. Go ahead and try to sum this infinite series. The sum of this infinite series is the first term, which is 4, times the rate, the common ratio of 0.6, raised to the, oh, my apologies, I got ahead of myself. Let's answer this question over here. A sub 1, we just said it's 4, right? So a sub 1 is 4, and the common ratio is 0.6. My apologies for that. So the common ratio is 0.6. Can we find the sum? Yes, we just answered that because it's less than 4. So we'll go ahead and input this into the infinite geometric series question. The 4, sorry about that, the first term goes on top of the fraction. And then we take 1 minus 0.6 on the bottom, 1 minus r on the bottom. So that's how we find the sum of this. So this ends up with 4 over 0.4, which comes out to be 10. So the sum of this series is 10. And of course we can continue to multiply by 0.6 to get each of the next terms. So if you need to pause the video and calculate each of these by hand. If we ever needed to, or if we ever asked you to come up with these terms, just keep multiplying by that common ratio which you identified and you'll be able to find those terms. Okay. Most importantly, our sum is 10. We're going to get real close to 10. So don't do what I do and rush right through. Make sure you pause for a second, take a look at what the first term is, take a look at what the common ratio is before you even determine if you even need to do the work. Question 4. I always need that first term, so let's go ahead and calculate that first term. That happens when I input this first input value of 0 in. So that's 1/2 to the 0 power, which is 1. And my common ratio is obviously the thing being brought to the power, so that means r equals 1/2. Pause for a minute, make sure that 1/2 is less than 1. So 1/2 is less than 1. The absolute value of 1/2 is less than 1. So we're good there. We are going to have an infinite series sum. And the formula for this is 1, that's the first term, over 1 minus 1/2, that was my common ratio. So 1 divided by 1/2, which we already saw is 1 times 2 over 1, which is 2. So the sum of this infinite series is 2. And then finally, we're going to find our first term. Actually, we're going to double check. Let's check the ratio first, right? Why even bother looking? Is the ratio 4/5, r equals 4/5, is the absolute value of that less than 1? It is a fraction less than 1. It is a fraction less than 5/2. So we are good. We are going to have the sum of an infinite series. And this formula says that I need the first term and the common ratio. So let's continue with that. The first term is when I input this first value in there. So that's 20 times 4/5 raised to the 1 minus 1 power. 4/5 to the 0 power is 1. So my first term is 20. So that means the sum of my infinite series is 20 over 1 minus 4/5, or 20 over 1/5, or 20 times 5 over 1, or 100. That's the sum of that infinite series. Okay? So the formula for this is good. Unfortunately, we can't jump to our calculator, but we'll use the tools that we have, and you will have those formulas available too. So go ahead and try your homework and let us know if you have questions.